Swayam Prabha. Digital India. Educated India.
Namaskar. So, in last session we were discussing about the Mason's rule. So, we will continue our discussion from that point onwards, and we will also see the state equation in the today's session. So, let us discuss first the Mason's rule which we were discussing in the last session. So, what we discussed about the Mason's rule, that this particular formula was derived by S. J. Mason when he related the signal flow graphs to the simultaneous equations that can be written from the graph. The existence of non touching loops in signal flow graph increases the complexity of this formula which was given by S. J. Mason. But what happens that generally in most of the system which you see in real time do not have non touching loops. So, in this way the application of Mason's rule is easier for those kind of systems, and for those kind of systems we find that the Mason's rule is very easy to use than the block diagram reduction. So, let us see what was the Mason's rule. So, suppose if C s is the output and R s is the input Laplace transforms. So, the transfer function of the system can be represented as C s upon R s, which can be provided with the help of Mason's rule as sigma k T k delta k by delta. So, sigma is nothing but the summation symbol, k is the number of forward paths in the signal flow graph, T k is the particular the kth forward path gain, and what is delta? Delta is 1 minus summation of loop gains, that is individual loop gains, plus summation of non touching loop gains when you take 2 at a time, minus non touching loop gains taken 3 at a time, we take the summation of that also, plus summation of non touching loop gains taken 4 at a time, and so on. So, delta will give you the loop gains related to individual loop gains as well as the non touching loop gains when you take 2 at a time or 3 or 4 and so on at a time. Now, what is delta k? Delta k is the delta for that part of the signal flow graph which is non touching with the kth forward path. So, this is the rule which was given by Mason's. Let us try to understand how we will apply this particular rule with the help of one example. So, let us take one example, say if the signal flow graph is like this, where you have from here you have a input say R s, and then you have the output say C s, and the transfer functions are like y 1 for this set, then z 2 you have a loop which is say minus y 1, then y 3 you have another loop which is minus of z 2, and then this is minus of y 3, then z 4, and this is a unity gain, the transfer function. So, this is the signal flow graph. If you get, the first thing which you have to find out is forward path gain. So, if you see in this particular signal flow graph, you will have only one forward path, there is no any other forward path available. So, your forward path gain is equal to take y 1 then Z2, Y3, Z4. So, this will be the forward path gain for the signal flow graph given. Now, next is we need to find out how many individual loops we have. So, here we will have 3 individual loop. What are those individual loops? One is this one. So, first one will be minus of y1 z2, second would be minus of z2 y3, and third one will be minus of y3 z4. So, these will be the 3 individual loops which you will find. Now, next is you need to find out the pairs of non touching loop. So, if you see in this particular signal flow graph, and if you only draw the loops, so there will be 3 loops which you will see. So, this is Z2 minus Y1, Y3 minus Z2 and Z4 minus Y3. So, out of that, if you remove the middle one, you will get 2 sets of loops which are not touching to each other. So, in that case, the value of non touching loops will be equal to the value of the transfer functions, that is, let us write in the next slide. So, the total gain of non touching loop would be minus Z2 Y1 into minus of Y3 Z4. So, minus minus will become plus and you will get Z2 Y1 multiplied by Y3 Z4. So, this is what you will get when you have 2 non touching loops. Now, next we need to find out the other non touching loops. So, if you see this signal flow graph, you will not be you will see that there is no any non touching loop, which means there is not more than 3 non touching loops you can see in this particular signal flow graph. So, set of 3 or 4 non touching loops are not available in this signal flow graph. So, finally, the delta which you can write is 1 minus summation of the individual loop gains. So, individual loop gains you have got like we discussed. So, what we can write? We can write minus of Z2 Y1 minus of Z2 Y3 minus of Z4 Y3, which you will get from this particular individual loops, and then you will have set of 2 non touching loops. So, this will become Z2 Y1 into Y3 Z4. So, this is what you will get as part of your delta. Next is that we have to see how many loops which you can find which are not touching the forward path. So, if you see this particular forward path, all 3 loops which you can see in the signal flow graph are touching the forward path. So, in that case, what you can write? You can write delta 1, because we have only one forward path, equal to 1, because we do not have any loop which is not touching the forward path. So, now what you can do? You can now compile the value, that is the transfer function of the complete system, that is C s upon R s. What you can write? Now, you can write T k into delta k. So, what is the forward path gain you have? Y1 Z2 into Y3 Z4, delta k is 1. So, anyway, that is you can write multiply equal to 1, or it will remain same. in the denominator you will write the value of delta. So, what is the value of delta? Delta will be 1 plus Z2 Y1 plus Z2 Y3 plus Z4 Y3 plus Z2 Z4 Y1 Y3. So, this is the transfer function which you will get from the signal flow graph when you apply the Mason's rule. So, I hope you can now do the calculations related to finding out the transfer function for other signal flow graphs. Now, let us talk about first order differential equation, and we also call it as a state equation. Why? Let us understand that particular concept. So, an nth order differential equation can be decomposed into n first order differential equations. So, the first order differential equations are simpler to solve than the higher order ones. The first order differential equations are used in analytical studies of the control systems. So, now let us take one sample differential equation. Say this is very common equation which you might have seen when we discuss the series RLC circuit and having the external voltage source connected. So, we can write R into I t plus L di by dt plus 1 upon C integral I dt equal to force, that is E t. So, what is R? R is the resistance, L is the inductance, C is capacitance, T is the current in the network, E t is the applied voltage. So, in this case E t is the forcing function, and what is T? T is the independent variable, and we will consider I t, that is current, as a dependent variable or unknown, which we need to determine by solving this differential equation. Now, let us assume integral of I dt with another variable, say x 1 t, and then we write dx1 t by dt as x 2 t, which is nothing but equal to I t. So, if you put the values x 1 and x 2 in this equation and you simplify, what you can write? X 2 is nothing but dx 1 by dt, which you can get from these two equations. So, you can simply write x 1 x 2 t is nothing but dx 1 by dt, and the di by dt is nothing but dx 2 by dt. So, which you can write, and if you take other terms on the right side, you can write minus 1 upon L c, and integral I dt we know we are representing it by x 1 t. So, we will write minus 1 by L c x 1 t minus this will become minus r by L x 2 t plus the L will come in denominator, then plus 1 by L E t. So, the equation which is written in R, I and E terms is equivalently represented in the form of x 1 and x 2. So, if you see this particular equation, this is basically first order equation where dx 2 by dt is written in terms of x 1 and x 2. So, in general you can write this, the concept which we just discussed, you can extend it for nth order system. So, what we can write? D to the power n y by dt n plus a n minus 1 d n minus 1 y dt n minus 1 and so on, plus a naught y t plus f t is the equation. So, what we will do? We will assume that the a 1 to a naught to a 1 and a n minus 1 are not the function of y 2 y t, means they are the constants coefficients. So, what we can do? We can replace y t with x 1 t, dy by dt as x 2 t and so on. So, that the x n, that is the nth variable, which we can define as d n minus 1 y by dt. So, when you represent the individual component as a variable, you can simply write with the help of this equation that dx1 by dt is nothing but equal to x2t, d2xt by dt equal to x33 and so on, and the last, that is dn xt by dt, can be represented as the individual components of x1 to xn minus 1 with the help of the equation which we have. So, what we can write, x and t by dt, that is dx and t by dt, can be represented as minus of a naught x 1 t minus a 1 x 2 t and so on, and the last you will get plus f t. So, whatever we have considered as a new variables, we have put them into this particular equation, and when we simplify, we can write the dx n t by dt as the summation of other components. So, the last equation which we obtain is received by equating the highest order derivatives terms to the rest of the term. So, the set of the first order equation which we get, in that the variables which you have defined like x 1, x 2 to x n, we call them as state variable. Why we call them a state variable? Because first let us understand what is state. State of a system refers to the past, present and future conditions of the system. Now, it is convenient to define a set of state variable and state equations to model the dynamic system. Here if you see the variable which you have defined like x 1, x 2, x n are the basically the variable which define the previous equation are the state variable of the nth order system, and the first order differential equations are the state equation. Now, what is the definition of state variable? So, state variable must satisfy the following conditions. So, at any initial time that t equal to 0, the state variable, that is x 1 t naught or x 2 t naught, define the initial states of the system. Once the input of the system for time t greater than 0 and the initial states just defined are specified, the state variable should completely define the future behavior of the system. So, the variable which you have seen x 2, x 3 and so on are somehow defining the derivative of the previous variable. So, with this you can specify the system performance, that is present or future condition of the system. So, that is why these are called as a state variables. Now, state variable of a system are defined as a minimal set of variable, that is x 1 to x n, in such a way that the knowledge of these variable at any time say t naught and information on the applied input at that time t naught are sufficient to determine the state of the system at any time t greater than 0. So, if you have knowledge for related to these state variable at time t is equal to 0, you can specify the system state for any time t greater than 0 with the help of these state variables. So, in state space form, these n state variable you can define it as x dot t is equal to a x t plus b u t. X dot t is nothing but the dx by dt of the individual state variables. So, which we just saw. So, here dx 1 by dt is equal to x 2 t, you can write as x 1 dot equal to x 2 t. So, when you compile all the equations which you just saw in this slide, then you can represent them in matrix form as x dot t is equal to a x t plus b u t, where x t is the state vector. So, if there are n state variable, you will have n rows in that state vector, and you will say x t is nothing but x 1 t, x 2 t to x n t. Now, what is u t? U t is the input vector. Say if there are n input variables, then the input vector will have, say if there are p input variables, then you will have input vector containing p elements. So, u t you can write as u 1 t, u 2 t up to UPT. Now, what are the coefficients? So, coefficient matrix A and B you can define as some variables A11, A12 and so on. So, A matrix will be n cross n matrix and B will be n cross P matrix. Now, let us talk about the output equation. An output of a system is a variable that can be measured, but a state variable does not always satisfy this requirement. Let us understand what does it mean. Say for example, in case of electric motor, state variables can be like winding current or rotor velocity and displacement. So, these are measurable quantities. So, that is why these variables can be qualified as an output variable, while on the other hand, if magnetic flux is also considered as a state variable in case of this electric motor, you cannot take the magnetic flux as a output variable, because you cannot measure the magnetic flux directly using any operation. So, that is why the magnetic flux does not qualify to be a output variable. Now, in general you will write output variable as a algebraic combination of the state variable. So, suppose if the system we just now described as d n y by d t n plus a n minus 1 d n minus 1 y by d t n minus 1 and so on. So, if you consider y t as an output, so in that case you can simply write y t is equal to x 1 t, because y t is considered to be one state variable and it is also considered to be a output variable. So, you can write y t is nothing but the set of if there are set of q output variables. So, y t will be the output vector containing q terms. So, starting from y 1 to y q. This also can be represented as a set of matrix. So, y you can write as C x t plus d u t, where C is again one matrix which is n cross q matrix and D is the matrix having dimension of q cross p. So, what we have done so far, we have presented the concept and definition of state variables and state equations for linear, continuous data and discrete data dynamic systems. We have also used block diagram and signal flow graph methods to obtain the transfer function of linear systems. Now, in the next session what we will do, we will use the signal flow graph concept to extend in the modeling of the state equation and the results which we will use in the state diagrams. The basic characteristic of state variable formulation is that the linear and non-linear systems, time invariant and time varying system and single variable and multivariable system can be modeled in a unified manner, while transfer function on the other hand are defined only for linear time invariant system. So, with this we can close our today's discussion. We will continue our discussion while we start modeling the multivariable system, where you will see multiple input and multiple output and how you will analyze those set of models. Thank you.